surrounding it, actually very close, is fairly densely populated. They really did kind of build this thing in the middle of this community. And each of these little homes around here had their own private garden where they grew stuff. And after the fire went out, and after a while, well, a year or so passed, and things kept growing. And among these things that appeared were like a two-eared corn. These are tomatoes that I wouldn't want to eat. And of course, my favorite is this guy, the shark seagull. Okay, that's photoshopped, but these are real. It really was a terrible accident, and the area remains totally uninhabitable now. Let's start off, though, talking about simple things like isotopes. We will talk about atomic symbols, because we'll use those a lot, and then get into radioactive particles. So, we have said since day one that elements were defined by the number of protons in their nucleus. Doesn't matter how many neutrons you have, how many electrons you have, only the number of protons. That's the atomic number. Periodic table, it's typically shown up top somewhere. 6 is carbon. The atomic symbol, we said, had three things. One is the symbol for the element. The second one was the mass number. Now we'll use mass number a lot today. Remember, mass number is the sum of protons and neutrons in the nucleus. We write that as a superscript before the symbol. Finally, the atomic number, or number of protons, goes down here as a subscript before the symbol. When we have different types of the same element, that is, the same element, so the same atomic number, but different mass numbers, we said that those were called isotopes. For carbon, we said there were three major ones: carbon 12, 13, and 14, and they differ in the number of neutrons that they have. Now, radioactivity is going to have to do with isotopes. We're going to start with one element, transmutate it into another, etc., etc. Kind of an interesting process. The whole concept was discovered many years ago. French scientist, 1896, working on phosphorescence. And in phosphorescence, you use photographic plates to measure the light that's coming off. And somebody in the lab inadvertently had a jar of uranium salt and set it down on top of one of the photographic plates. And by George, when they went and developed it, the plate was ruined. Now that was a big deal in those days because you couldn't just run to Walgreens and get more film. You had to make these suckers by hand. It was, really complicated. So this was disturbing. Word got out that this had happened, and a number of people started working, trying to come up with an explanation for what happened. Among those people were Marie Curie and others, and basically they found that from this jar of uranium salts, there were three types of particles that were being emitted. Okay? Three types of particles that were being emitted. And they called them alpha, beta, and gamma. Now they differed both in mass and in charge. Beta particles were basically negatively charged. They looked for all the world like an electron. Now, Why an electron is living inside the nucleus, they had no clue. But this was a -1 charge. Alpha particles they found were 2 protons and 2 neutrons, +2 charge. This is equivalent to a helium nucleus, and quite often it's abbreviated as He. The third particle was neutral. It was very energetic, and this was called a gamma particle. Gamma particle basically looked like, an X-ray or a very high energy photon. Neutral, but again, very high energy. The 3 particles do differ in their inherent energy, also in what it takes to stop them. Alpha particles are big, they're heavy, they're slow. You could stop an alpha particle with a sheet of paper. Most beta particles are much more energetic. This is supposed to represent 1 centimeter of lead. Typically, that's what it takes to stop it. Gamma particles, very energetic. This is supposed to represent 10 centimeters of lead. And still, with that, some of them are energetic enough to just go straight through. We can do gamma particles all the way from surrounding stars in the deep universe, whatever. Very high energy. To measure radioactivity, we use a simple device called a Geiger counter. Geiger counter has a tube. You pull a partial vacuum, put a little bit of gas in there, this is argon, and you have a window. Now you have an anode and the cathode. Cathode's the outside. Ionizing radiation comes in the little window here. As it does when it interacts with one of these atoms of the rarefied gas, basically it ionizes it and you get a little lightning bolt from top to bottom. The electronics count the electric pulses and you get, the typical sound. Now that's kind of neat, I suppose. Everyone carries around their own Geiger counter, don't they? And this is a Geiger counter. This is the little tube right here. And this is a bottle of uranium salt, just like was fogging up the thing, except this is depleted. Okay? They take all the good stuff out of this, and you're just left with this thing that's, according to the US government, non-radioactive. All right, well, let's look at that. Push the button. You can hear a click every now and then. Those are gamma rays coming in from somewhere. I don't know, I hear something. Depleted uranium might not have uranium-235 in it, but it most certainly is not non-radioactive. They actually use depleted uranium to make armor-piercing bullets. And in the Gulf War, apparently the desert is just full of these things. It's not a good thing, but it's depleted, right? Right. Okay. Let's talk a little bit about where these things come from, how they come out of the nucleus, and some of the magic that's involved. Let's start off with alpha particles. As we said, it has a mass number of 4, 2 protons and 2 neutrons. It has a charge of +2. This is my pretend nucleus here. In my pretend nucleus, I have 12 protons, 12 neutrons. If this was to eject an alpha particle, remember it's just like a helium nucleus. 4 of these little balls will get together. They will leave. We have 2 protons, 2 neutrons. We have dropped the atomic number by 2 because we lost 2 protons. And we have dropped the mass number by 4 because we have 2 protons, 2 neutrons. So, atomic number drops by 2, mass number drops by 4. And this just flies away. One element that does this quite dependably is uranium. We just heard it. Uranium-238, mass number of 238, can lose an alpha particle. When it does, it's going to form a different element. Now, the element that we form, we have lost 2 protons from the nucleus, so the atomic number of our new element has dropped. It is now 90. The mass number of our new element has also dropped by 4 mass number units. The element, the symbol, we have to look at our periodic table. We're looking here for an element with the atomic number of 90, and that's thorium. So we put our symbol in. This is thorium. Once again, the mass number started at 238. We lost 4. We're at 234. We have converted uranium-238 to thorium-234. This is called a nuclear equation. In a nuclear equation, you don't have the same numbers and types of atoms, obviously, because they've changed. But what you do have is the sum of the mass numbers is the same on both sides. 238, 4 plus 234, 92, 2, and 90. Protons add up, mass numbers add up. Any questions? All right, well, let's do an equation. Thorium-230 loses an alpha particle. We're going to write the nuclear equation. First of all, to get the atomic symbol, we have to look and find the atomic number for thorium. It's right here at 90. So we start off with thorium-230, atomic number 90. The problem said this is going to lose an alpha particle. Here we go. Mass number is 4, atomic number is 2. Again, equivalent to a helium with no electrons. If our atomic number drops by 2, that gives our new one 88. Again, we look at our periodic table and we see who is 88. Oh, over here, radium. So we put the symbol in, Ra. Our mass number started at 230. We lost 4. We are at 226. We started with thorium-230, wound up with radium-226. Balanced nuclear equation. Any questions? Let's do another one. Polonium-214 loses an alpha particle. Write the equation. Now, we need to know the atomic number. We're starting here at 84 for polonium. Go ahead and fill in the rest of the equation. Now, we don't have a periodic table we could use. Seems a shame, but Fill in what you can. We are losing our alpha particle. That means the atomic number will drop by 2. Instead of 84, we're at 82. All right, we look at our periodic table, looking here for 82. And there it is. That's lead. We started at 214. We lost 4. We are at lead 210. Any questions?
Is it always going to lose 4 and 2?
Whenever you lose an alpha particle, this will drop by 4 units.
So it's
Always going to be that. All right, well, an alpha emission is kind of straightforward. We take a nucleus and we kick out something from it. All right? Beta particle emission is a little bit of magic. In a beta particle, a neutron, which is neutral, is going to actually shed an electron. Yeah. If you think about it, protons positive, electrons negative, put them together, you get a neutron, right? Well, not really, but apparently, sorta. When the neutron loses its electron, it converts itself to a proton. So we start with a neutron, 1 mass unit, wind up with a proton, still 1 mass unit, and we have a negative electron. Once again, 12 protons, 12 neutrons. Now in this, one of these neutrons is going to decide it's tired of being neutral and wants to be positive about things. So it sheds its negative charge, becomes a proton. We now have 13 and 11. And here's our negative beta particle. It's like magic. All right, let's look at a real case. Thorium-234, atomic number 90, is going to lose a beta particle. When it does this, one of these neutrons is going to be converted to a proton and an electron. All right, we form a proton from a neutron. That means the mass number is going to stay the same, right? The atomic number, however, is going to go up by 1. That's because it used to be neutral, and now it is a proton. So our new atomic number here is 91. We look at our periodic table. 91. There it is, PA. Not Pennsylvania, proactinium. Okay? So this is proactinium, symbol Pa. Now, the mass number, because the neutron converted to a proton, it hasn't changed. So we're still at 234. So what do we write for a symbol here? Well, it's a beta particle, right? So we'll call it beta. The mass number doesn't change, so for mass number, we'll put 0. And finally, atomic number? Well, remember, in a nuclear equation, this side must add up to the same as this side. This is 91. This must be -1. Thorium loses a beta particle, becomes proactinium. Any questions? All right, let's do one. Bismuth 210 loses a beta particle. What are we going to get? Bismuth is right here at 83. So bismuth, atomic number 83, 210 is our mass number. We are losing a beta particle. Mass number is 0. The, quote, atomic number is -1. That means the new element we form must be 1 greater than what we start with. So instead of 83, it's 84. These add up to 83. Okay, 84, who's that? Oh, we're here at polonium, PO. The mass number does not change, so this is polonium 210. Any questions? Interesting point. Polonium 210 is an alpha emitter. It also has the distinction of being the most toxic radioactive element that is known. 10 nanograms. Nano, remember, is 10 to the -9. So 10 nanograms will kill you. If you had 1 gram of polonium 210, you could kill, 100 million people. Yeah, pretty toxic stuff. It's also the KGB's favorite assassination method. Yep, 10 nanograms isn't much. Apparently, the Kremlin was having difficulties with a former KGB agent, and so they invited him to tea, gave him 10 nanograms of polonium 210, and he died 3 weeks later. This was 2006. Yeah, bad stuff. Like I said, polonium 210 is an alpha emitter. When it loses its alpha particle, the atomic number drops by 2 to give us 82. 82 is, there it is, lead. So our symbol is Pb. We drop this from 210, lose 4, lead 206. Now, different alpha particles have different energies. This one is particularly energetic. That's why this is so terribly toxic. You might wonder exactly where this toxicity comes from, because alpha particles are so big and ugly and slow. It comes from the fact that if you inhale this, so you ingest your 10 milligrams, it winds up in your lungs. Now remember, we could stop an alpha particle with a piece of paper or a cell nucleus. If it happens to be the cell nucleus that stops this alpha particle, it mutates the heck out of it, and in 3 weeks you're dead. It's pretty bad stuff. All right. This is neon. So far we've looked at the heavy elements down here only. I put this in just to show that sometimes lighter elements do the same sort of thing. This is neon 19, and again it loses a beta particle. Go ahead and let's figure out what we get. We start with an atomic number of 10. Our beta particle has an atomic number of -1, meaning that this must be 11. 11. Oh, there it is. This is sodium we're making. So, Na, the mass number does not change. So this is sodium 19. All right. Any questions? Well, a gamma particle. With a gamma particle, you start off with a nucleus. You're going to wind up with the same nucleus. It's just going to emit this particle. Now, it has virtually no mass, the particle. Again, it's just like a very energetic light ray. It comes about when a nucleus, typically when a nucleus loses an alpha or beta particle. When that happens, the nucleus is unsettled. Like, oh my gosh, what just happened? And because it's unsettled, it kind of jiggles around a little bit, and away comes a gamma particle. So as it settles down after losing a particle, the gamma is the energy that it emits. Again, you start with the same element and end up with the same element. You're just missing this gamma particle. Gamma particles, like I said, can be very energetic, travel clean across the universe. Any questions? Well, let's look at a list here. On the exam, typically there's an equation, nuclear equation of some sort, and you're simply expected to put the product or the particle, or in some cases, the starting material. So let's do these. Here we have radium-226. We're going to lose an alpha particle. That means the atomic number is now going to be 86. If we look around to find 86, 85, 86, there it is. It's radon. So, radon is our element. 86 is going to be our atomic number. The mass number is going to drop from 226 to 224. I'm sorry, 222. Higher math, Any questions? All right. Chlorine-39 loses a beta particle. The mass number is going to stay the same. The atomic number, start at 17. On this side, it's going to be 18. Look at our periodic table. 18 is right here. It's argon. So we are converting chlorine into argon-39. Lead-214 loses a beta particle. It's beta, so the mass number is the same. It's a beta particle, so the new atomic number is one more, 83. 83, let's see, where's that? Here we are back at bismuth again. So this is going to be bismuth, atomic number 83, mass number 214. And our last one here, we have radon-86, losing an alpha particle. Mass number is going to drop by 4. Atomic number will drop from 86 to 84, making this polonium again. Our product will be polonium 218. Got it. Any questions? Well, this brings us to our last tutorial of the course. I know that's a very sad moment. This is called nuclear equations. It's very simple. You have a reaction that's shown. Sometimes the particle is missing. Sometimes this is missing. Sometimes whatever. You get it. In this particular thing, we are losing an alpha particle. Now, instead of using He here, I used the Greek symbol alpha. Again, they're interchangeable. He is a little clearer because you look at that and say helium, no electrons, 2 and 2. Okay, but this is alpha. So we're starting at 26, we're losing 4. Our mass number is 22. We are starting at 12, we are losing 2. Our atomic number is 10. We look at our periodic table. You can see one right there. And let's see, we're looking for 10. There it is. This is neon. Any questions? All right, well, you know, we have done radioactive decay here now. We started with one element, we wind up with another one. In many cases, I'm sure you noticed, this is a process. You start with one, go to another, another. This is kind of a chart that shows the process here. These are atomic numbers here, and this is atomic mass here, or mass numbers. If we do an alpha decay, we're going to move over 4 mass numbers and drop 2 atomic numbers, whatever. So let's just see what happens to one of our friends, uranium. Uranium-238. Starts by losing an alpha particle to give thorium-234. That loses a beta to give proactinium. Another beta, and we're back to uranium. An alpha, we're down to thorium. Another alpha, we're down to radium. Another alpha, we're down to radon. Now, radon also loses an alpha particle, and that is somewhat problematic these days. That's because back when they were mining uranium like mad, uranium is a very small impurity in big rock. So you take the rock, you grind it up, you're left with lots of rock powder and a tiny, tiny bit of uranium. Well, what do you do with the rock powder that you have this mountain of now? Very simple. You make cinder blocks. What do you do with cinder blocks? Well, you build homes, you build schools, you build basements, etc. Now, because this still has trace amounts of uranium in it, this decay cycle continues. And depending upon how much you have in here, radon is formed. Now, radon is a gas. It's the first of these that's a gas. So it comes seeping right out of the brick and into your rooms, into your homes, and mostly into your basements. Basements are made either with very large rocks or with cinder blocks or something like them. These days, if you want to sell a home, you have to have your basement checked with a radon detector. And if you do have radon down there, you say shoot, because you have to put in ventilation and blow the stuff out and whatever. It's just a bother. Any questions? All right. We've seen the decay here, right? How long does this take? We measure radioactive decay using something called a half-life. The concept is pretty simple. If we start off with 100% pure uranium, uranium will change first to thorium. When your original sample, the concentration has dropped by 50%, you look and see how long that took, and that is the half-life. It's the time required for half of the original element to decay to the next element in line. Simple concept. An example, strontium-90 loses the beta particle. When it does, it forms yttrium-90. Again, the atomic number goes up by 1. This is a balanced equation. The half-life, the half-time required for this decay, is 10 to the 6 seconds, or roughly 30 years. So if we started with a gram of this, 30 years later, we would have half a gram. Simple concept. Now, if you happen to be a child of the 50s, this is something that is important to you, sorta. Because in the 50s, everyone thought it was such a neat idea to explode bombs in deserts. And they were just going off everywhere, okay? When they went off, they made one heck of a mess, and the mess was called radioactive fallout. One of the fallouts was strontium-90. Now, the reason strontium-90 was particularly bad is that it's isoelectronic to calcium. What do you use calcium for? Oh, building strong bones and healthy bodies, right? So, we set a bomb off in Nevada. It rains in Wisconsin. The cloud of radioactivity falls down, containing strontium-90. Cows eat the grass. Give the milk. And you give the milk to your children. Assaying baby teeth. Children of the 50s had 50 times higher strontium-90 than before they started blowing off bombs. Fortunately, half-life is 30 years. We basically lived through it. But yeah, it was there. Still is. For a long time. Half-lives vary a lot. This is on the order of billions of years. This is 1 second. This is just fractions of seconds. Some actual numbers. Uranium-238 and 235. Basically, you're looking at 1 billion years. So that stuff hangs around a long time. Thorium, 10 to the 10th years. Carbon-14, we'll talk about that in a moment. 5,700 years, strontium-90 we did. Iodine-131, 0.02 years, about 8 days. So it covers the entire spectrum. Now, just like strontium-90 was the plague of the 50s, In 1976, I believe, we had a power plant, 3 Mile Island. It melted down. When it did, 79 it was, when it did, there was a huge cloud of radioactive iodine that was released. Now, iodine is a bad thing because your body accumulates iodine to make thyroid hormone, so your thyroid gets very radioactive and you get thyroid cancer and die. Fortunately, you don't die because there's a simple fix. What they did when the plant melted down, they ran around and gave everybody potassium iodide pills. That loads your body with iodide, and you don't absorb from the cloud. So it works. Any questions? All right. Let's do a half-life problem. Cobalt-60. It's a beta emitter. Very energetic, used in nuclear medicine. Half-life of 5.3 years. I tell you that I go into the cabinet in the back room here and I find a 1 milligram sample. All right. After 15.9 years, what's left? Well, of course, there's an equation for that. And of course, we're not going to use the equation. Don't worry about it. You would choke yourself trying to get this in your calculator. Instead, we're just going to look at the problem and come up with a pretty good estimate. The half-life is 5.3. We're at 15.9. That's 3 half-lives. So we start with a milligram. After 1 half-life, we have half a milligram. After 2 half-lives, we have 0.25. After 3 half-lives, we have 0.13. So, I said something about going in the cabinet and finding this. Turns out that when Triton was built, somebody purchased a little sample of cobalt-60, which you're not supposed to do because it is a very powerful beta emitter. And so I looked at this little sample and said, oh my goodness. And I pulled out my trusty Geiger counter, and there was nothing there. Okay, so either somebody sold them a piece of sand, or it had been roughly 10 half-lives, and we're down to a tiny bit of stuff. Any questions? All right, there's one other aspect of radioactive half-life I'd like to talk about. Turns out that our atmosphere is full of nitrogen. Okay? Turns out also that we have a sun up there somewhere. And one of the things the sun does that nobody quite realizes is that it spits high-energy neutrons at us constantly. Now, our atmosphere protects us by absorbing some of this radiation. So, nitrogen-14, high-energy neutron from the sun, comes sailing in, they collide, and by George, the neutron sticks, hits the nucleus and sticks. When it does, it forms nitrogen-15. Well, nitrogen-15, however, is very, very unstable. And it is so unstable that the nucleus immediately breaks down. That's being unstable. And it ejects a proton and forms carbon-14. Okay. 14 plus 1, 14 plus 1, 7 zeros, 7. It's balanced. Now, carbon-14 is the radioactive isotope of carbon. It emits a beta particle with a half-life of 5,700 years. And when it does, it forms nitrogen-14 again. Okay. This is the basis of radiocarbon dating. Let's pretend that everybody in the room here is alive. Okay? As long as you're alive, you are breathing and eating. You eat things that contain carbon. Because of the upper atmosphere, a very small amount of that carbon will be carbon-14. Carbon-14 decays to give nitrogen-14. All right. But when you die, you stop eating and breathing. So, pretend that you're a saber-toothed tiger. You're walking around eating and breathing, right? That means that the ratio of C14 to carbon-12 is constant. Now, you die. After 5,700 years, one half-life, half of the carbon-14 that was in you has decayed. 2 half-lives, 3 half-lives, whatever. What you do in the lab is you measure the carbon-14 to carbon-12 ratio, and that tells you back when the thing stopped breathing. That is radioactive dating. Kind of neat. Any questions? All right, well, the formation of a beta particle was strange, right? Neutron decides it wants to be a proton. The formation of this next particle, called a positron, is even stranger. In positron formation, you have a proton that is tired of being positive, and so it sheds its positive charge as a positron. That converts it to a neutron. Now, what is a positron? Positron is a positive electron. A positively charged electron. Here's our nucleus, 13 and 11. One of these protons decides it doesn't want to be a proton anymore, loses its positive charge. This is our positron. It's a positive electron. This is the way you actually would write it. Proton, positron, neutron. In order to make the equation balance, the mass number on the positron must be +1. An element that does it is carbon-11. Here's the positron, forms boron 11. Now, how can you have a positive electron? It's called antimatter. Yeah, antimatter is real. A negative electron, a beta particle. Positive electron, positron. Now, if you ever saw Star Trek, Scotty was always worried about the matter and antimatter mixing because they annihilate each other, right? Well, they were right. They do. If we take a positron and an electron, allow them to touch each other, they annihilate and form two gamma rays. Now, this process is interesting because the gamma rays that are formed are emitted from the collision site in totally opposite directions. One up, one down. This forms the clinical basis of positron emission tomography. So, that's a person. This is a ring of Geiger counters. And they're looking for gamma rays. These are computers. Because the gamma rays from the collision are emitted in opposite directions, the computer is here watching for simultaneous emissions 180 degrees apart. So what you do in tomography is you take glucose usually, label it with fluorine 18. That's a positron emitter. When this emits its positron, it will instantly hit an electron, and as it does, you get gamma rays. So this is one, happens again, happens again. Your computer triangulates all these things, and it can tell you the exact point at which the labeled glucose is sitting in your body. Now, this is used to detect tumors, because tumors are very simple cells. They don't do oxidative metabolism, they only do glycolysis. So you feed somebody sugar, it goes straight to the tumor. So put your person in the middle of your ring here, have your computer gather up all the data. This is a real PET scan. This person has a very bad gastrointestinal tumor. PET scan. Positron emission tomography. Kind of an interesting use, isn't it? All right, let's look at another problem set. We have arsenic 70, atomic number 33, loses a positron. What are we going to make? Well, we are here. The atomic number will drop by 1. So we started at arsenic, we're now germanium. So it's germanium, atomic number 32, mass number 70. Krypton 77, again, positron. Our mass number will stay 77. We are starting at 36. We will drop down one more to 35, making this bromine. So bromine 77. What emitted this particle to give bromine 79? Well, the mass number is going to be 79, isn't it? We're at 35 here. We're going to drop down 1 to 36. I guess go up 1 to 36. This is krypton 36 is our atomic number, 79 the mass number, and there we are. And our last one, we're making iron 58. Our mass number will be 58. Our atomic number over here will be 27. And there it is, cobalt. Cobalt 58. Any questions? All right, let's mix them up because on the exam you can get any combination. Chlorine loses a beta particle. Mass number will stay the same. This will be what? 18 on this side. 18 is going to be argon, argon 39. Neon loses a beta particle. Mass number is still 19. This will be 11 on this side. 11, as you recall, is sodium. So sodium 19 is the product. In this one, sometimes I ask what the particle was that you lost. Our mass number is dropped by 4, atomic number by 2. Clearly, that's a helium nucleus. We are forming, there we go, simple helium. And our last one, plutonium-239, loses alpha. Going to drop by 4, drop by 2. That's going to give us 92, I think. And I didn't pay attention, but that's uranium-235. Uranium-235 is the fissile element that's used to make bombs. Plutonium is fairly easy to come by, actually. Simply decays to give this stuff. All right, how in the world does an isotope know what it's going to lose? It has to do with the neutron to proton ratio. This is the middle line. The black in the middle is called the, quote, line of stability. And things on the top have more neutrons and protons. These tend to be beta emitters. This side, we have positron and we have fission and alpha. So it just has to do with the ratio in the nucleus. All right, let's go to the fun part. We talked about the formation of carbon-14, right? We said that a high-energy neutron can hit a nucleus and stick. But quite often that nucleus is unstable and it breaks down. This is called transmutation. But if the products that you get are bigger, it's called fission. Nuclear fission is what gave us the gift of fission bombs. All right, so what we're going to do to make a fission bomb, and I'm going to tell you exactly how to do it, so you could go home and make one. You could. Transmutation, we said we get an unstable nucleus that splits. All right? Uranium-235 is an element that is known to do this. If we take uranium-235 and we take a high-energy neutron, it can come and hit the nucleus, form uranium-236. That's unstable, and the whole thing splits open. Here comes our neutron. There's 236, and it splits. When it splits, it forms two nuclei and three high-energy neutrons. These high-energy neutrons go back and do it again. And that's a chain reaction. In this cleavage that we just saw, we formed krypton and barium, and again, three high-energy neutrons. The energy that's evolved when this happens, 200 million electron volts, equivalent to 2 trillion degrees Kelvin. Lots and lots of heat and energy. Again, if we reutilize these guys and do the whole thing over again, that's called a nuclear chain reaction. Now, to show a nuclear chain reaction, typically people use mouse traps and ping pong balls. That's the official way to do it. These are little mouse traps. Each of them has 3 ping pong balls on them. This is somebody holding our ping pong ball. That's our neutron that comes in. You drop it in the hole. And whoosh! That's the chain reaction. Once again, the chemistry is simple. 235 to 236. We split huge amounts of energy and more neutrons. Now, in order for this to proceed in the chain reaction, you've got to have enough stuff there. If you have a little tiny bit of uranium-235, that's called a subcritical mass. And that means that once this happens, these neutrons that you make can sneak out. So this gets warm, but nothing really happens. But if we have a larger mass, we'll call it a critical mass. Virtually all the neutrons undergo this chain reaction, and we get uncontrolled fission. Let's watch. More ping pong balls. And that represents a critical mass. Lots of material, highly dense. If, however, we have low density, something like this, we can take a neutron, shoot it at this place, and just have it bounce right on through. Isn't that amazing? That must have taken them dozens of times to get that video. But nonetheless, it's amazing. In a nuclear power plant, you want to control the fission. You do that by putting down control rods that block the neutrons. They absorb them. If you want more power, you raise your rods, you get more fission. You want to shut it down, you drop the rods down, they absorb, no fission. We will return to this concept in just a minute. But the other use for fission, of course, is bombs. This is a video, kind of striking, from 1952, I believe. And what we're going to do, we're sitting in the desert in Las Vegas with a cannon. We're going to shoot an atomic bomb out of this cannon. Yeah, let's watch. They're all so pleased with themselves. there it goes. Goes down the range about 3 miles. And there it is. Now, when something like this happens, first thing it hits is a shock wave. And they put these things in the desert there to record. The second thing that happens is the blast wave. Here it comes. Oops. Oh, come on. I apologize. Afterwards, all the dust that has been kicked up sucks back into the infamous mushroom cloud. And as this was happening, here are these guys, half a mile away, recording every bit. They're all dead now, of course, but nonetheless, they recorded it for us. This particular bomb has a yield of 1 kiloton. 1. Typically, these days, if a yield is a kiloton or 2 or 10, it's called a dud. Yeah. This entire bomb fit in this barrel. This is what it looks like. That's it. You can tell it's an authentic picture. Here's the engineers that designed it. Pocket protector, comb over, whatever. 1952. But yeah, this is the whole thing right there. It's astounding. And that is about the smallest you can make them. How do you make it? The simple type is called a gun-type fission bomb. This was our very first. What you have is a gun barrel. At one end, you have half a critical mass. At the other end of our barrel, we have the other half of our critical mass. When they're apart, nothing happens. You set off the explosion here. This slides down. We make a critical mass. About a microsecond later, 10 to the minus 6 seconds later, that happens. This was our very first one. This was about 10 kilotons, still in the dud range. Also in Las Vegas. I say don't try this at home because you could. If you have 2 halves of critical mass, you simply put them together, hold them there for a microsecond, and it happens. That's why people get so upset when third world countries are making uranium-235. But nobody makes bombs like that anymore. They're too expensive, too cumbersome. Instead, we use something called an implosion bomb. Implosion bomb, we use plutonium. We have a subcritical sphere here in the middle. This is surrounded by traditional high explosives. Connecting all these are little detonators that must go off precisely at the same time. That's what makes this a difficult bomb to make and why people make gun bombs instead. All must go off at exactly the same instant. We start with subcritical mass here. One way to make it critical is to increase its density. So here it is. We set all these things off at the same time. The shock wave goes down, compresses the core, and there it goes. An implosion bomb. What's it look like? A soccer ball, about the same size. These are the high explosive parts. This is the plutonium pit. Goes in the middle, about the size of a baseball. There, maybe a softball. That's a plutonium pit. Here's the casing. Put these together and you get a bomb. Now, interestingly, if this is sitting on one shelf and this is on another, it's not a bomb. That's a trick that we used, the Russians used, Israel uses it. They have one shelf with the pits, one shelf with the casings. They're not bombs. But you pick one up, put it in there, and it is. As we saw with our artillery shell, you can make these things very small. This is about 10 kilotons worth. It's designed to be worn by a person. Infiltrate lines, set it off, blah, blah, blah. This is the Russian version. This is a briefcase. Yes, it is. Called a briefcase bomb. This is about 100 kilotons worth in a briefcase. When the Soviet Union collapsed, the soldiers guarding this sort of stuff weren't paid, and so they went home. And now there's a lot missing. So somewhere somebody's got up to 50 of these things in their basement. If it's you, don't mess with them. All right, that's fission. That's the little brother. The big brother is fusion. In a fusion reaction, we're going to take two elements. In this case, we're using deuterium, that's hydrogen with one proton, and tritium, hydrogen with two neutrons. We are going to take these and squeeze them together very, very hard. When we do, they will make helium. We will emit a high energy neutron and a huge amount of energy. This is the chemistry that the sun uses to shine brightly in the sky. The sun takes hydrogen, squeezes it to make deuterium, squeezes it to make an isotope of helium, squeezes it again to make helium. At every step, you get a huge amount of energy. Of course, the first thing they did once they realized this was figure out how to weaponize it. This is a hydrogen bomb. Now, in a hydrogen bomb, we have our deuterium and tritium in here. And we need something to get it really hot and compress it a lot, right? Push them together. What do you use? Recognize that? That's an atomic bomb. That's a fission bomb. So that's the detonator for this baby. The very first one, we destroyed a perfectly wonderful island in the Pacific. The yield was 10 to 12 million tons of TNT. These are really serious bombs. This is the Russian bomb, 50 megatons. It's a gorgeous explosion. We're standing 50 miles away. Imagine all the radioactive debris that's kicked up. Originally, this was supposed to be a 100 megaton bomb, but they dialed it down because they did their calculations, and turns out that the plane that drops this could not possibly get far enough away if it had been 100 megaton. It would have been consumed in the cloud. So, you might ask why in the world people would need to make a 50 million ton bomb. Turns out that the reason is very simple. Making the bomb, yeah, they could do that. But the guidance in those days was so bad. The idea was close counts. So, we realized that too. Our guidance wasn't great either. And major cities like Chicago surrounded themselves with interceptor missiles. This is Lakeshore Drive. There's the Field Museum. And these are Nike missiles. They each had a kiloton atomic warhead in their nose cap. Each one. This map, the entire lakeshore, most of the suburbs, yeah, those were all missile batteries. The idea was, you see this missile coming in over Lake Michigan, everybody gets a shot at it, and you hope somebody hits it. And because it's a 50 megaton bomb, doesn't matter where it lands. Okay. Well, there's another side to radioactivity, and that is nuclear power plants. This is a classic nuclear power plant. This is a cooling tower, not the reactor. That's the reactor building right there. Their operation is really not that much different than a coal-powered plant. Basically, what you're going to do is use the fission to boil water, make steam, turn a turbine. Things are very hot in here. You have one closed loop here with very hot water. You have more pumps, steam. You have more pumps. These are all separate loops, so it's fine. Unless something goes wrong. Now, there are two things that could go wrong. Remember I said to use control rods to control the flux of neutrons, how fast the reaction goes. If you happen to bend a rod, it doesn't go down its hole, does it? If a pump goes out, we can't cool it fast enough. And when that happens, we get Fukushima. Now, Fukushima today looks something like this. This is reactor number 1. It is filled with water, seawater. The water is very radioactive. They have no clue what they're going to do with it. But it's just sitting there. That's a good thing, actually, because it turns out that water is very effective at moderating neutrons. So it absorbs the neutrons, keeps everything relatively cool. Because of that, water is used to control nuclear waste. Now, I'm sure as soon as you realize that in a reactor we have these spent rods that aren't performing like they used to, and you said, gee, what am I going to do with these? Well, of course, the first thing that occurred to you was build a swimming pool and put them in there, right? Yeah, that's what they did. Called Morris, Illinois. Giant swimming pool filled with nuclear rods. Now, the problem with this, however, is that we have these long half-life things that are formed. We still have uranium left as well. And all these reactions are going on in the swimming pool. Well, that makes this hot. It also makes it blue. That's kind of neat. That's the effect of the water Chirkonoff radiation, I believe. Neutrons going through there form this eerie glow. Nonetheless, so when your rods get old, you got to put them somewhere, so you build a swimming pool, put them in there. You pump water out of the pool, let it cool, pump it back in, constant, constant, constant. Somebody realized that that's not a great method. This is a map of all of the nuclear waste sites in the country. That's Illinois. Yeah, we got a bunch, don't we? Not just Morris, we got a bunch. This represents metric tons back in 2013. Once again, we go from 3,000, none, 130, Illinois, 900 or 9,290 tons of radioactive cores stored in our state. We are number one in the world in something. People decided in the late 80s that that was a bad idea. Swimming pools weren't going to work forever, too dangerous. So somebody at the Atomic Energy Commission decided they were going to buy a mountain. Didn't have to buy it, actually, we already owned it. Called Yucca Mountain. The idea was tunnel underneath this 1,000 feet, take all the radioactive waste in the country, put it in the hole. It's under a mountain, right? Right. So they did. Huge tunnels going down, way, way down. They designed special vehicles to transport this stuff. Massive trucks. The radioactive stuff is in here. These are warm. So yeah. And they made this giant set of tunnels. Their plan looked like this. They were going to tunnel in here, go down, and this is where they were going to put the high-level waste. Okay, if you're a politician, I guess that makes sense. However, nobody stopped to ask, why is that mountain there? Well, mountains are formed when tectonic plates collide. One rides up over another, and you get a mountain. Which means that underneath this mountain, the tectonic plates are broken. It's a fault line. Yeah. So you dig down 1,000 feet and you put your high-level radioactive waste on a fault line. That's earthquakes, guys. Not only that, but when somebody pointed that out finally, they looked around in Nevada and said, well, gee, below this, 1,000 feet, that's the water table. So you're stacking your radioactive waste on a fault line directly above the water table. Believe it or not, they finally convinced themselves, and we have this mountain now with these huge tunnels in it that you can't use. But it's a nice mountain. Nice tunnels, too. So what do we do now? Well, we're back to swimming pools, right? After it sits in the swimming pool for, 1 million years or so, it decays to the point that you can put it in concrete containers and just kind of let it sit in the desert. Hopefully they'll cool over time. You can also just put it in barrels and scatter them in cornfields. That works too. Nuclear waste is the number one problem with nuclear power. However, along comes fusion. Now, just like this was the big brother of fission bombs, fusion powers the sun. Again, you take hydrogen, make helium. Nowhere in this process do you form radioactive waste. The process that we use, deuterium and tritium, you get hydrogen, that's it. I'm sorry, helium, that's it. And a neutron, and lots of energy. Trying to tame this, however, has been difficult. The original design looks something like this. This massive machine. The fusion chamber is down here somewhere. It takes, well, what you do, you have a ring of magnets, very high vacuum, and you're going to fill this with deuterium and tritium. Then you heat it up. You heat it to the point that you get plasma formed. Now, it takes lots of energy to heat these gases up to make plasma. But once they're formed, plasma is charged, and you can control where it is with this array of magnets. They've been working on